Good evening, Clydesdale. Misconceptions and little bits of confusion, mainly in astrophysics and, as you will see, elsewhere as well. Let me just get rid of this annotation that I don't want. Okay. So we're going to be looking at a few different ideas across various parts of science. I'll be looking at how the universe is expanding. I'll be looking at the concepts of matter and dark matter, rocket science and how it is that we can, for instance, launch a space telescope and park it at a particular point in space. And I'll be having a quick look at quantum mechanics. All of these are areas of science that, for one reason or another, have produced a great deal of misconceptions and a great deal of confusion. And I'll be addressing each of them in turn, using slides that I've put together for various other talks that I've given over the years. But one thing to bear in mind is this quote from Einstein. The most incomprehensible thing about the world is that it is comprehensible. In other words, for some reason or another, primates like us were able to come out of the trees, start walking on two legs, and eventually got to the point where our brains developed so that we are able to comprehend the universe in which we live. So perhaps rather than worrying about the fact that there are misconceptions, perhaps we ought to celebrate the fact that there is actually a lot we do understand about the universe, even though there are still points of confusion along the way. So let's start with the first topic. We live in an expanding universe. And a question I've often had is, well, if it all started with the Big Bang, where should I point my telescope so I can see where it all started? Because we often see cartoons like this, where there's a bright flash and then we get a whole load of galaxies forming. And it gives the impression that the universe started at one particular point. And perhaps we can look in that direction and see what was where the universe began. But that is a very serious misconception that completely misunderstands the way the universe works. And that's because there are so many cartoons like this, which show the universe starting as a point and then expanding to fill the observable universe that we see. This only works if we can step outside the universe and look back at it, which we can't do. The Big Bang, as far as we are aware, was the start of everything. And therefore there wasn't one particular place where it started, because the Big Bang happened everywhere. And a similar question is, well, if the Big Bang happened 13.8 billion years ago, then if the James Webb Space Telescope can look back in time, will it be able to see this bright flash? And again, will it have to point in a particular direction in order to see the bright flash of the Big Bang? Because the James Webb Space Telescope is a time machine. It can look back in time. Therefore, is this possible? And again, that's a misconception as to the way James Webb works. It only is a time machine in the sense that the further it looks out into the universe, the further back in time it's looking. But that doesn't mean it'll be able to see back 13.8 billion years to the Big Bang. There's a limit to how far light will get you back in time. In other words, the earliest light we will ever see is the light of the cosmic microwave background. We won't ever be able to see further back in time than that. A few years back, during COVID lockdown, I told you about a challenge in which I set myself a how far can I image with my camera challenge. And I looked at a particular patch of sky where I expected to find a very distant galaxy, a quasar. A quasar is just the name given to a galaxy with a very bright nucleus. And I expected to find it, according to reports that I'd read, inside that rectangle there in the constellation of Draco. And when I blew that up, I found there is the quasar, indicated by the two red lines. Not a very spectacular image. Only 1 pixel or so is catching the light from this very distant quasar. But what's amazing about this is simply the distance it's at. And because we live in an expanding universe, the more distant parts of the universe are receding from us at higher and higher velocities, according to the Hubble law. And that means when it comes to trying to work out how far a very distant object is away from us, we have to remember that the light has travelled for a long time to reach us, and during its journey from the distant galaxy to us, space has continued to expand. To the best of our knowledge, space has been expanding ever since the Big Bang and continues to do so to this day. So trying to work out, well, how far is it to these distant galaxies? Well, that's a rather tricky problem, because it's a bit like a swimmer swimming through water where the water is dragging the swimmer backwards, or an ant moving along a rubber band where the rubber band is being stretched. Light moving through space where space is expanding is not something we're used to thinking about, so it's no real surprise that there are plenty of misconceptions in this particular area. And the only thing we can actually measure about a distance is the redshift, how much the light is stretched from a distant galaxy. We can't actually measure the distance, we can't actually measure the time taken for the light to reach us, but we can measure how much the light has been stretched by looking at the spectrum from a different distant object. And redshift is not something we're used to thinking about. Scientists can calculate a redshift, and from the redshift we can calculate a distance. But it's not really intuitive, which is why, again, it's difficult to get your head around what all this means. But the redshift of this particular object that I photographed, this quasar, it had a redshift of 4.3, which puts it at these particular points here on our graph of how we go from redshift, how much the light has been stretched, to distance. And notice there are 3 distances here, so I'll get rid of the lines and just concentrate on those 3 numbers. The blue is how far away was the object when the light was emitted. So for this particular quasar, it was 5 billion light years away from Earth when the light left, the light that eventually ended up in my camera. The light has been travelling for over 12 billion years, about 90% of the age of the universe. And during those 12 billion years, the universe has continued to expand, which means now the light has arrived, the object itself, the quasar, is now about 25 billion light years away, according to these calculations. But if we think of these numbers, the distance to this object has changed from 5 to 25 billion light years, but it's only taken 12 billion years to do that. So if its distance has increased by 20 billion light years in a time of less than 20 billion years, that means it's been receding from us greater than the speed of light. And yes, that is correct. It's a little bit unusual, but that is how the universe works. Here I've calculated what is the recession velocity of this quasar from the time the light left, the blue dot, more than 12 billion years ago, to what the velocity is now, the orange dot on the right hand side. And you can see that the recession velocity of this object originally was slowing down, but then after a few billion years it started to speed up again. So this is again something that's completely counterintuitive, because we are simply not used to thinking of an object moving from A to B over a given distance in a given time. We're not used to the idea of the distances continuously changing as we are travelling from one point to another, the light travelling from the quasar to the Earth. For instance, if we were thinking about the distance between Merseyside and Lanarkshire, well, it's about, 200 miles or so. It was 200 miles last year, it's 200 miles now, and it will be 200 miles next year. And if we were to travel from Merseyside to Lanarkshire, that distance would be 200 miles, regardless of if we travelled very quickly in a plane, or relatively slowly in a car, or if we walked. It would still be 200 miles. But that's not how the universe works, because the goalposts are continuously changing. The distances are continuously changing. So the length of time, or the distance between any 2 points, will depend on how long you take to get from one point to another. That's why thinking about an expanding universe gives rise to so many misconceptions. If we were to plot how the light gets from that quasar to us, the light left the quasar some 5 billion light years from us. That's when the light left the quasar. 0 is the Big Bang, and up here, 13.8 billion years later, is us here and now. So how did the light get from the quasar, originally at this distance, to us? Did it simply take the shortest distance it could take? Well, it would like to, but the universe is expanding. So actually, because the universe is expanding at twice the speed of light or thereabouts for this quasar, the light that's trying to get to us was actually dragged backwards. And again, there's no surprise that there's confusion here, because this is just completely counterintuitive. That light is trying to reach us, but because of the expansion of the universe, the light is getting dragged backwards. So for the first few billion years of the light's journey, that light, far from getting closer to the Earth, was actually getting further away from the Earth. And it wasn't until a time of something like 4 billion years or so that finally the light started to make some headway and then slowly started getting closer and closer and closer to Earth. As I say, confusion abounds over this, and there's no surprise whatsoever because it is so far removed from our everyday lives. We're used to the idea that distances are generally fixed, and if we want to go from one point to another point at a particular velocity, then we can calculate how far we travel, how long it takes, and distance divided by time is the speed at which we're travelling. But those simple rules that apply for travel in the UK does not apply when we're thinking about light travelling across the universe. So confusion abounds, and it's completely understandable why. Let's have a look at another misconception, the idea of dark matter and black holes. Black holes are often visualized like this, as if it was a funnel. And some people get the impression that a black hole is a sort of two-dimensional structure down which things fall. And therefore people ask, well, what happens on the other side? What happens if you go down this funnel, and where does this funnel lead? But that's a misunderstanding, simply because this is a representation of, in a sense, what a black hole would look like if we lived in a two-dimensional universe, whereas black holes in fact are three-dimensional. They are effectively spherical, usually. And so that gives the misinformation, if you like, or at least the confusion, or definitely the misconception, that if we were to look at an image like this, taken by the Event Horizon Telescope, this orange glow here is the matter swirling around the black hole. This gives the impression that the black hole, again, is something like the funnel we saw before, and if we were to go vertically down this central object, we would end up in this funnel and end up somewhere else. So this misrepresents the fact that a black hole is actually a spherical object, even if it happens to be surrounded by perhaps a disk-like structure, a so-called accretion disk of matter waiting its turn to fall into the black hole. So this is an EHT, an Event Horizon Telescope image of the supermassive black hole at the centre of galaxy M87, and also we've imaged a similar structure around the centre of our own Milky Way, a supermassive black hole, rather smaller but a little bit closer than a neighbouring galaxy and therefore easier to image. So I appreciate there's not much to see in these images, but even this one image alone can be easily misinterpreted. And partly that's Hollywood's fault, because they always seem to indicate that as soon as a black hole is formed, it will suck in everything around it, and nothing is safe from a black hole. As if the gravity from a black hole is something very special compared to the gravity from any other object, like a planet or a star. So you could say, well, if black holes are a source of gravity and they suck in everything, well, why don't stars do the same? A star is a gravity well. It's a large mass which tends to pull on anything around it. For instance, our sun pulls on everything in the solar system. But that doesn't mean the sun is going to eat everything in the solar system. The Earth is quite happy at its distance from the sun because the Earth is orbiting. And if things move in an orbit, they don't necessarily get sucked into the star that's keeping them in orbit. And the same is true of black holes. Just because a black hole exists doesn't mean all matter will be sucked into that black hole. It depends on how that matter is moving. Like, for instance, the matter in the accretion disk orbiting around the black hole. When we think about the composition of matter, there's a whole lot of stuff we know about and a whole lot of stuff we don't. So we know about, for instance, the stars and the gas and the dust. But the question is, most of the matter in the universe appears to be this 84% that doesn't fall into the category of all of the stars and all of the hydrogen and helium and other gases and bits of dust and other things. This is the so-called dark matter. But dark matter doesn't mean this stuff. The Horsehead Nebula, for instance, is not dark matter. The reason we have misconceptions over dark matter is because it's not a very good name for what we're talking about. Dark matter isn't matter that looks dark. The Horsehead Nebula looks dark because it's absorbing light from more distant stars. The glow in the background that you can see is being absorbed by this dark nebula here, and that's why the light isn't getting through. So it's a dark nebula, yes, but it's not what we refer to as dark matter. Dark matter should really be called invisible matter because it doesn't emit light and nor does it absorb light. So we really ought to be calling it invisible matter, but we never got that chance and the name dark matter has stuck. Dark really refers to our ignorance rather than the fact that the matter absorbs light. So if that's not what we mean by dark matter, then how do we see it if it's invisible? Well, we can't see it directly. We have to rely on other evidence. For instance, we can look at how stars move in a galaxy. And without dark matter, we would expect the stars close to the edge of a galaxy to actually move relatively slowly. But actually what we see is stars, even towards the edge of the galaxy, seem to move a lot faster than we would expect. And if they're moving faster in an orbit, that means something is keeping them in orbit. There's much more mass there, much more matter than we can account for just by looking at all the visible matter from all of the stars that are glowing. So we deduce the existence of dark matter from its gravitational effect, not like a dark nebula from the fact that it absorbs light. We know dark matter is out there for a number of different reasons. I've shown you one example, the way galaxies rotate, but there are other reasons for thinking that dark matter exists. If we think about the very early universe, at the moment everything in the observable universe is inside a sphere something like 100 billion light years in diameter. But we know the universe is expanding, therefore everything used to be a lot closer together. And if we wind the clock back far enough, everything we currently see in the observable universe used to be only centimeters or so in distance apart from each other. So I like to think of it as a cosmic golf ball. A golf ball that had small variations in density, just like the dimples in a golf ball. And those very small variations in density, eventually, when the golf ball expanded until it's the size it is now, the golf ball of the observable universe is now 100 billion light years in diameter. It took billions of years for that to happen. But the dimples, the small variations in density, eventually gave rise, as we can see in this simulation, to the structures we see in the universe. Here, the lighter colours indicate denser and hotter regions of the universe. So what started off relatively uniform, gravity over billions of years took hold of these small variations and produced denser and denser regions. So here we see these hot spots, which are the formations of clusters of galaxies and superclusters of galaxies, which seem to sit on these filaments in this web-like structure. A structure in which there are filaments and also voids, which are relatively devoid of any galaxies. When we look out into the universe, this is the sort of filamentary structure that we see on the largest of scales. But this simulation only works and only gives us the universe we see if we take into account dark matter. If we leave dark matter out of the mix, the universe doesn't clump enough. And that's another piece of evidence that dark matter exists. It's not because we see dark clouds out there. We infer it from its influence on other parts of the universe that we can see. Yep, most of the universe is dark. Some 84% of the matter that's out there is matter we can't see. It's a bit embarrassing to say we can only see a tiny fraction of the universe. And we still don't really know what dark matter is. Let's have a look at a third misconception, the idea of rocket science and how we can park a spacecraft at a particular point in space. I've taken a few slides from a talk that I call It's Not Rocket Science, because rocket science is made to sound really, really, really difficult. Okay, building a rocket is a technical challenge, but the science behind it, how you go into orbit, how you change from one orbit to another, how you send spacecraft out to explore the planets, for instance, that's not as difficult as people would make out. For instance, Newton, hundreds of years ago, figured out that if you could send something sideways with enough velocity, for instance, put a cannon on top of a mountain and fire the cannonball sideways, if you give it enough horizontal velocity, it will go into orbit. Newton knew that hundreds of years ago, and the maths required to do the calculations is not that difficult. All that really matters when we're trying to think about orbits is this concept here. The closer you are to the sun, or the closer you are to whatever object is keeping you in orbit, let's assume we're talking about planets going around the sun, the closer you are to the sun, the stronger the gravitational pull, and so the faster the planet moves. So for instance, this green planet is closer to the sun than the red planet, so it's got a stronger pull to the sun, so it moves faster. The red planet is further from the sun, the gravitational pull from the sun is weaker, and so the planet moves more slowly to stay in orbit. Notice that yes, the red planet has further to go, but it's not simply that it takes longer to go around the sun because it's got further to go. It is actually moving slower in terms of kilometers per second because the gravitational pull is less, so it doesn't need to travel as fast in order to stay in orbit. That concept is really all you need to know about orbital mechanics, or if you like, rocket science. Everything else is just the application of the maths to allow you to calculate the numbers. So let's see how that allows us to park a spacecraft. Let's assume that the green is planet Earth. Planet Earth goes round the sun in 1 year. If an object is further away from the sun, it will have a period of more than 1 year. For instance, Mars is a lot further away from the sun than the Earth, so the Mars takes a lot longer than 1 year to go round the sun. But what if the red orbit was close enough that it's not only being pulled towards the sun, but it's being pulled towards the Earth as well? In other words, those two arrows indicate that it's getting pulled towards the sun, the yellow arrow, and it's also pulled towards the Earth, the green arrow. There is an orbit at a distance, which I'll come to in just a second, such that the combined pull of the sun and the Earth makes the red object not go round the sun in more than a year, but it goes round faster with a period of 1 year. That means the red object would go round the sun in sync with the Earth. Because it's being pulled always in the same direction towards the sun and towards the Earth, the red object takes the same length of time to go round the sun as the green object, which is very different from what we saw before, remember. So that means we can, in principle, place something there. So I'm going to replace these green circles and red circles with the planet Earth and the point which we call Lagrange 2. We won't worry about what the other Lagrange points are. Let's just concentrate on L2. L2 is the point such that the combined pull of the Earth and the Sun means that L2 goes round the Sun with the Earth. So from the perspective of the Earth, L2 is fixed. It's always fixed on the opposite side of the Sun. L2 is always hovering above the midnight point of the Earth. Because remember, noon is on this side where the Sun is, so midnight is on this side of the Earth. L2 is hovering a distance above midnight. The scale, well, I haven't attempted to draw this to scale. The distance from the Earth to the Sun is 1 astronomical unit, and the distance from Earth to L2 is approximately 1% of that, 0.01 astronomical units. So quite definitely not to scale. But the point is that we can understand why there's a point that always goes round the Sun in sync with the Earth, and therefore we could place a spacecraft there, and that spacecraft would move with the Earth and always be on the opposite side of the Earth from the Sun. It is simply a question of the combined pull of the Sun and the Earth. We can get more complicated and say, well, what's going on if we were to have a look closer to what's going on around the point L2. This particular colourful donut that you can see here is a way of visualising what's going to happen to a spacecraft close to the point L2. Think of these contours as being the height above sea level, for instance, where red is a high point and blue is a lower point. And think about an object, if we placed it on this donut, how that ball would roll around. Because a ball will always want to roll downhill. Red is high, remember, blue is low. So if we have a look more closely around what's going on around L2, let's take that to one side. If we have a look around L2, we can see that if we were to go in the direction of downhill, well, from here, downhill means coming away from Earth or going towards Earth, but not going up in this diagram or down in this diagram. Remember, red is high, so downhill actually points towards this point, or from the other side, downhill points towards this point. So that point there, the L2 point, is not the top of a hill. It is not the bottom of a well. If you go in two directions, you go downhill, but if you go in the other two directions, you go uphill. What do we call such a structure? It's a saddle point. Mathematicians would represent it like that. I tend to think of a great example of a saddle point being a Pringle. Next time you're eating a Pringle, just have a close look at it. You notice it curves one way in one direction, but the other way if you go at right angles to that. So, take-home message, the James Webb Space Telescope, which is parked around L2, is sitting on a Pringle. We can place objects in orbit around that particular point L2. For instance, Gaia has just finished its mission. It's sitting at L2. James Webb is currently at L2. Other spacecraft have been at L2, and more spacecraft will be sent to L2 in the future. It's a great place to park on the opposite side of the Earth from the Sun. And for the James Webb Space Telescope, that keeps the telescope nice and cool, which is important for an infrared telescope. It'll be kept in orbit, but it will need a little bit of a nudge every once in a while, because you can see from this diagram that if it starts to drift towards Earth, it goes downhill and goes faster and faster and faster. So if left to its own devices, it might drift downhill and end up crashing on Earth. But if we give it a nudge, whenever it starts to drift towards Earth, we just give it a little nudge back again, then we can keep it at the L2 point. So the James Webb Space Telescope and other telescopes in the vicinity just need a little station-keeping nudge every few months. Very little fuel is used. Most of the time it orbits around L2 quite happily. If it does drift towards Earth, it needs a little nudge to get it back again. Let's have a look at our final misconception. Quantum mechanics. How do we describe not the world of the very, very large, but the world of the very, very small? Let's face it, the universe is made up of lots of structures, including atoms, so we really ought to understand what atoms are if we want to understand how planets and stars and other things are put together. We tend to think of an atom as looking like this, a nucleus with electrons buzzing around it like bees. But that doesn't tell us that all of the electrons have different energies. So we really need a slightly better picture than that. This one looks a little bit more like a solar system where lots of electrons are going around a central nucleus at different distances, a bit like planets are at different distances from the sun. That at least satisfies our requirement that different electrons have different amounts of energy, but clearly it's not really a solar system because some of these objects, well, we seem to have 2 planets in the same orbit here, like having 2 Mercuries, and we seem to have 8 objects as if we've got 8 Venuses or something like that. An atom isn't really a 2-dimensional structure, much like the solar system mainly is 2-dimensional. The electrons in an atom are actually in shells, but we still find it more convenient to draw them in a 2-dimensional sense as if they were a bit like a solar system. If we're describing atoms, given that we really shouldn't be thinking of little billiard balls moving around through space around a nucleus, we should really think of them, according to quantum theory, as being, where am I likely to find an electron? If this electron exists in an atom, well, it's really a sort of a cloud, a sort of probability cloud. Where am I likely to find that electron? And these shapes here, these clouds, are patterns that tell us the likelihood of finding an electron from a nucleus, which is the point in the middle of each of these little patterns. There are 8 examples of how an electron might be found close to the nucleus of an atom. That helps us visualize where an electron is likely to be, and it's not simply at a given fixed distance as our previous couple of models might indicate. But that's part of the problem with trying to understand atoms, is how do we actually describe an atom? We can come up with a whole load of words in which we can talk about electrons and nuclei, and we can talk about the energy levels of an electron. But all of the English words that we can come up with to describe how an atom behaves, all of these words like particles, waves, orbits, spin, energy, they all have a connotation which don't necessarily translate directly into how atoms behave. And if we wanted to draw a picture of an atom, well, in essence, we can't. Any picture that looks a bit like a solar system is wrong. And even an attempt to draw pictures which are, where am I likely to find an electron? That doesn't really, if you'll excuse the pun, give us the full picture. It's a way of representing some aspect of how the atom behaves, but it's not everything. So if words and pictures have their limitations, how should we describe atoms? And the answer you're not going to like. The answer is, well, we use maths. And in order to teach students how the world works on the scale of the very, very small, on the scale of subatomic particles or atoms or molecules, we have to rely on maths, but of course we use words to explain the maths, and occasionally we use pictures to try and explain the words we're using. Maths always seems to work, but words and pictures sometimes help, but sometimes get in the way. So there's a huge amount of confusion when people try and understand quantum theory and what it tells us about how the world works, simply because words and pictures are not enough. And the maths, the maths doesn't speak for itself. The maths is messy and it takes ages to understand what the maths is telling you. And if only maths works and not words and pictures, again, there's no surprise that there's a lot of confusion and plenty of misconceptions over what quantum theory is actually telling us about how the world actually works on the smallest of levels, or how it might work in very compact systems, not necessarily atoms, but compact systems such as Well, for instance, neutron stars or black holes. So again, it is no surprise that there's confusion. There's no surprise that there are misconceptions, simply because the concepts are so alien to us. We can't expect our day-to-day experience to help us understand how an atom behaves, in much the same way that an expanding universe is not something that we're used to thinking about in our day-to-day experience. It's only been in the last 100 years or so that we knew the universe was expanding. It's only been the last 100 years or so that we've realized that quantum theory tells us how things work on the smallest of scales. We haven't yet had time to get used to these ideas. 100 years is not that long. It's only a few generations. The maths is horrible, and it takes quite a few years to understand the maths. One of the architects of quantum theory says, "We wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language." And this has been a barrier ever since. We can't easily change the English language to cope with atoms, so we have to continue with English, and we have to use maths to tell us what is actually going on. Another architect of the quantum theory, atomic physics has shown that atoms have no meaning and can only be understood in experimental measurement. In other words, an atom is just a concept we use to try and understand how the world is put together, and quantum theory allows us to calculate how things happen. So, for instance, we can use quantum theory to build ourselves a microscope. Here's an image. Notice the scale is less than 1 nanometer on a side. 850 picometers is a little less than 1 nanometer. And on this scale, we're seeing a few atoms of carbon. So quantum theory allows us to build microscopes that allow us to see atoms, or at least see smudges, which we interpret as being atoms. Bear in mind that at this magnification, a grain of sand would be about the size of the moon. And whenever I see a microscope image like this showing atoms or molecules, I tend to think of William Blake's poem, "To See a World in a Grain of Sand." So quantum theory is confusing. It takes, well, a lot of thought, and it takes a lot of time. A lot of what quantum theory is telling us doesn't agree with common sense. And if things don't agree with common sense, it is very easy to get confused. And if things don't agree with common sense, it's very easy for misconceptions to arise, because we tend to rely on common sense to tell us when something sounds right or something sounds wrong. But unfortunately, that doesn't really work with quantum theory. So I've given you an indication of a number of different areas: an expanding universe, which is counterintuitive because we're not used to the idea. The ideas of dark matter, and to be honest, we don't actually know what it is. It is possible that dark matter is black holes, but dark matter is not simply dark nebula that are absorbing light from more distant objects. Rocket science is not rocket science, despite what a rocket scientist may tell you. Rocket science only sounds complicated because the maths gets in the way. If you take the maths away, what's left is not so bad. And in principle, we can understand, for instance, Lagrange points, parking places for rockets or spacecraft sent up beyond the Earth's gravity, beyond the Earth's direct influence, beyond Earth orbit. We can place things around the sun such that they appear to be stationary relative to the Earth. The maths can get very awkward, but the concepts are not that difficult. Quantum theory has always been a source of confusion, and it has been for the last 100 years, and it's quite possible it will continue to be a source of confusion for the next 100 years or more. I've tried to outline some of the misconceptions that have cropped up and some of the questions that I've had when giving talks about the nature of the universe or the nature of quantum mechanics. I might have made those misconceptions clearer. I might have muddied the water. Either way, I hope you've enjoyed the talk. Thank you very much for listening.